Hello students, Dr. Regmi here. Let us start our chapter 6 today. The chapter 6 is about energy changes, reaction rates and equilibrium. Okay, let me first give you a little bit background on why we are studying this chapter and then we can dive into the material. Okay. So we know that chemical reactions, they do have two facets. Okay, how much energy changes do occur during a chemical reaction, how fast or slow a chemical reaction can be. So these two things are related with the chemical reactions. Okay, because in the nature we find some of the reactions, they produce tremendous amount of energy, right? If you burn fossil fuel, if you burn octane or butane fuel, you get very high energy, you flame, right? We can use the gasoline, we can burn the gasoline and use the energy to run the cars, right? Our body, the human body or any animal or plant system, they consume, right? They consume food and they release energy. That released energy can be used to do the manual job like walking, running, swimming, or doing work in the field, right? Why certain reaction, they produce this huge amount of energy, and on the other hand, there are some reaction that will need energy to do the reaction, right? Certain reactions are exothermic reaction, while others are endothermic reaction. So in order to understand, to classify the reaction, right, whether the heat is released or whether the heat will be needed to do the reaction, we want to have that kind of information. That's why we are learning this chapter here. Okay, so let us look on with some introductory words, right? What is energy? You might have heard energy is the capacity to do work. We eat food, right? That food is metabolized. We get energy, and that energy we can use to do some work. Work is always whenever we apply force, we let the object move on a distance, we call it in math work. Okay, so energy can be of two different types: potential energy or kinetic energy. Okay, so potential energy is the stored energy, right? If you see a ball at the top of a hill, or water is in the reservoir just behind the dam, these two are examples of potential energy. They contain energy, it is in the stored form, right? So as soon as you open the dam, right, as soon as the ball is allowed to release, right, allowed to roll down the hill, now it will gain the momentum, it will run faster, right? Now the stored energy will be converted into the energy of motion, and the energy of motion is defined as kinetic energy. We call it kinetic energy, right? So potential energy is the stored energy, while kinetic energy is energy on the motion of particles. Okay, some examples are potential energies. Example is chemical energy. It means those energy that are stored in the chemical bonds of the reactants or products, we call them potential energy. Okay, and heat is the example of kinetic energy, the thermal energy. Okay, because it is the energy produced due to the moving particles. So you can see that the potential energy or the kinetic energy, we have a law of conservation of energy to govern these processes. Okay, so the law of conservation of energy states that the total energy in a system does not change. Though you can transfer the potential energy into kinetic, you can make the kinetic energy transform into potential energy. Okay, the energy can be transferred from one form to another form, but energy cannot be created or destroyed. Okay, so that is the law of conservation of energy. So now, as I mentioned, the energy stored in chemical bonds, either they be in ionic or covalent bond, that is the form of potential energy. Because chemical bonds in the compound are the location where the energy is stored, and any stored energy is called potential energy. Okay, so the energy, either due to the position of its existence or due to the bonds they have, is the potential energy. And you will see that a compound, and we are trying to see the connection of energy in the chemical reaction. Okay, we want to look on that aspects. So a compound with lower potential energy is more stable than a compound with higher potential energy. Okay, that's why the reactants would like to form the product. Generally, the products will have the lower potential energy than the reactants. Okay, so reaction will be favored towards the forward direction, right? Because from high potential energy, you are going towards the lower potential energy, and lower is better. Lower gives you more stability. Okay, so that's what we see. Now we are going to look some units of energy. What are the convention units we use? And then we will explore more into the relation of energies in the reaction. Okay, so we measure energy in calorie, or we measure energy in joule. Okay, a calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree C. So definition gives us 1 calorie. Okay, generally a calorie is used in industrial areas, right? Or when they have to calculate the nutritional caloric value of a nutrition, they go by calories. Okay, other areas we measure energy in joule, and we have symbol J for that. Okay, a joule is another unit of energy, and that calorie and the joule are related by this relationship. 1 calorie, okay, lowercase c is here, 1 calorie is equal to 4.184 joule. Okay, this relationship will be provided in the exam. Okay, so in the formula sheet. How 1 joule is related with 1 kilojoule? It is the metric system. 1000 joule is equal to 1 kilojoule. Okay, similarly 1000 calorie is equal to 1 kilocalorie, right? And 1 kilocalorie is equal to 4.184 kilojoule. So actually, if you remember one of them, the metric units you already know, you can convert from one unit into another. Okay, let's try that with one question here. Carry out each of the following conversion. I have 45 joule to convert into calorie. Okay, so here the calorie is lowercase c. Okay, sometimes you might see uppercase c. The uppercase c is also the unit of calorie. Okay, 1 uppercase c is equal to 1000 lowercase c calorie. Okay, that might be something confusing, so I have not written it here. Okay, but if you come across that, just remember. Okay, so let's try here. I have 45 joule, so I'm going to start with dimension analysis or unit conversion, you can say. Okay, I'm writing 45 joule, and then I know that 1 calorie is equal to 4.184, right? Did I write that correctly? 4.184 joule, right? So I have here 1 lowercase calorie, okay, calorie by 4.184 joule. Now I can cancel the joule with joule. Now 45 divided by 4.184 gives me 10.76 calorie. And now you can report that answer in 2 sig fig because 45 is 2 sig fig. So I'll write 11 calorie for the answer. Okay, that's simple. Let's try another question. 55 kilocalorie to kilojoule. Okay, I do not remember other units. Okay, something that I remember is 1 calorie is equal to 4.184 joule. This one I have memorized it, so I want to use the one that I have memorized to work on this problem. There are more than one way of doing it. Okay, so 55 kilocalorie, I can convert that into 1 kilocalorie is equal to 1000 calorie, right? This is the metric unit. And then 1 calorie is 4.184 joule. Now the question is asking me kilojoule, right? So I cannot end up here. I have to go for one more conversion. I need to put joule on the bottom, kilojoule on the top. How are they related? I know 1 kilo of something is 1000 of that base unit. So 1 kilojoule is 1000 joule. 1 kilogram is 1000 kilogram, right? Sorry, 1000 gram, my bad, 1000 gram. So I can place it there. 1 kilojoule is equal to 1000 joule. Now joule cancel out, calorie cancel out, kilocalorie and kilocalorie cancel out. On the top I will have 55.6 times 4.184. On the bottom, I can divide this and that. They can cancel because 1000 on the top, 1000 on the bottom. Let me try this in the calculator. On the calculator, 55.6 times 4.184. When I multiply that, I get 232.63 kilojoule. Now I can report that answer in correct significant figures. I have 3 sig fig, right? 3 sig fig in the starting number. So I can write this as 233. Now I got 3 sig fig kilojoule. Okay, so I got kilojoule. Or if you remember that 1 kilocalorie is equal to 1 kilojoule, because you are multiplying by 1000 on both sides, right? It means 55.6 kilocalorie is directly you can write 55.6 kilocalorie times 4.184 will give me kilojoule. And the answer will be the same, 233 kilojoule. Okay, either way, you will get the same answer. Okay, so with that, let's look on how can we calculate the energy, the caloric energy in a food. Okay, so let me connect this with something that we know. Like any food that you buy from the store, on the food packaging, on the back side of the food packaging, you will find something like nutritional facts, right? It will talk about the serving size, the serving, how much servings are there in per container, and then there will be calories calculation on a table. You will see the percentage given, total fat, sugar, sodium, this, blah, 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 right? So all that information we get in the nutrition facts. So we can use that nutrition facts to convert certain calorie into another. How much does that whole container of that product have calories in them, right? So in general, we have this table given out. Okay, if we have a food type, okay, if the food is carbohydrate, or some percentage of it is carbohydrate, then when you burn 1 gram of carbohydrate, you will get 4 kilocalorie. Okay, per every 1 gram of carbohydrate, you will get 4 kilocalorie energy. Or if you look on this unit, per every 1 gram of carbohydrate, when it metabolizes, when it burns, you will get 17 kilojoule. Okay, so this is the table that will be given to you in the exam if such question come. So this table gives you the typical energy value for 3 different types of food. Okay, for fat, every 1 gram of fat will be equal to 9 kilocalorie of energy. Every 1 gram of protein will give you 4 kilogram of energy. Okay, you see how the fat gives us more energy. Okay, so because it's 9 here, right? So we can use this information to figure out how many calories does a particular product, particular food item has it. Okay, so let's read this question. A cup of whole milk contains 13 gram of carbohydrate, 9 gram of fat, and 9 gram of protein. If that is the case, then how many kilocalories does a cup of whole milk contain? Okay, so let's calculate. We should be able to see this table and be utilizing that. So you have carb in 1 cup of whole milk. Carb. So let me write carb. Okay, you have 13 gram of carbohydrate. Each 1 gram of carb, okay, gives you, and here the question is asking for kilocalorie. That's why I will use these units over here. Okay, kilocalorie per gram. I have to use these numbers. Let me see if I can bring eraser. No. I'm lost here in my pen. Okay, so 1 gram of carbohydrate gives me 4 kilocalorie of energy. Okay, so I use that relation. 1 gram and gram of carb cancel out. I have 13 times 4. Okay, we will come up with a number. Similarly, I have 9 gram of protein, right? Each gram, 1 gram of protein gives me 4 kilocalorie of energy. I took this value conversion factor from the table. So I have here 9 times 4 is 36 kilocalorie. Now let's work on 9 grams of fat. Oh, I skipped that. Fat was in the second. Anyway, so 1 gram of fat is 9 kilocalorie from the table. So gram of fat cancel out. I have 81 kilocalorie here, 36 kilocalorie in the protein, and I have 4 3s 12, 4 1s are 4, 1 5, 52 kilocalorie from the carbohydrate. The question is asking us how many kilocalories does a cup of whole milk contain? It contains all of these, right? It has that much of carbohydrate, this much of fat, and that much of protein. So let's add all together. I have 52 plus 36 plus 81. All together, I got 169. 169 kilocalorie is the sum of these energy from each of these different kind of food. Now you can see 13 2 sig fig, 9.02 sig fig, 9.02 sig fig. So I want to report this answer into sig fig. So I write 170 kilocalorie in 2 significant figures. Okay, so the final answer is 170 kilocalories are present in 1 cup of whole milk. Okay, is that clear? Okay, so since the question is asking for kilocalorie, we took these values. If the question has asked us kilojoule, we would use the next values, right? Values on the next column. So just be careful on that, which value to take in. Okay, so with that, let's now jump into the energy relation in the reaction. Okay, whenever we do chemical reaction, it means we are bringing the molecules together, right? We are letting them to react. During that case, in the reactants, the bonds in the reactants will break down, right? And new bonds will form, and that will result into new products. Actually, this is all happening, right, at molecular state, at molecular level. Whenever a reaction is taking place, the reactants bonds are broken down. The products bonds are forming in, right? This is the process that takes place. So during the breaking of bond, we always need to supply the energy. Okay, the bond breaking process always requires an input of energy. Let us suppose you have a chlorine molecule, and here it is shown the Lewis structure for the chlorine molecule. Okay, and you want to break this bond between the two atoms of chlorine. Okay, this is a covalent bonding, right? You have a sharing of electrons, and that forms a covalent bond. Now, in order to break that bond, you need to supply energy. Okay, you need to input energy to break that one. And when you break that, since it is a single bond, it is formed by sharing of two electrons. That one electron will go to the first chlorine, the second electron will go to the second chlorine, and we have two chlorine atoms, right? Separated atoms. Okay, so to cleave that bond, to break that bond, we need to supply energy of something like 58 kilocalorie. Okay, to break 1 mole of chlorine molecule, we need to add that much energy into it. Similarly, if you have two separate atoms of chlorine, okay, down here we have two separate atoms of chlorine atoms, you want to combine them, you want to make a bond between them to make a chlorine molecule. Now, in this case, whenever the bond forms, it will release energy. Okay, so when there is a suitable condition, these two chlorine atoms come closer, they form a bond, then now in this case, 58 kilocalorie of energy per mole will be released, will be produced as a result of the bond formation. Okay, so in short, we have to understand that bond breaking process is you have to supply energy. Bond making process or bond formation, it will release the energy. Okay, the process will release the energy. Okay, now to understand in a chemical reaction, to keep track of whether the process is releasing energy or it is inputting, it requires energy. To keep track of that, we look the changes in the energy. And whenever it is related with chemical reaction, we call it enthalpy. Okay, it is a new term here that we will be working on. That enthalpy is also known as heat of reaction. Okay, when a particular reaction is taking place, whether the energy, the total energy will be released or total energy will be, we have to supply, it depends on that enthalpy value. We represent the enthalpy change by the letter delta H. Okay, enthalpy, H is for enthalpy. Heat is for Q, we write Q for heat. Okay, H is not directly heat, but it is known as heat of reaction. Okay, because in advanced classes you will learn that there is a relation between delta H and Q. Okay, but for now, we understand that in a chemical reaction, the energy will be absorbed or released. Okay, the total energy will be absorbed or released in a reaction. Whenever the energy is absorbed, in that case, we call that process endothermic. Okay, endo means input, in, right? Endo means input. You need to put the energy, so energy is absorbed to do that reaction. whenever it is endothermic process, the value of delta H, it will have a positive sign in it. So delta H is a positive sign quantity if we have endothermic reaction. Okay, and we will be clear with the example in our next slide. And whenever the energy is produced, whenever the energy is released, we call it exothermic reaction. Exo means out. Okay, understand. Exothermic means out, energy is released. Endothermic means in, you have to supply the energy, you have to input. Okay, input and output. So exothermic reactions will have the delta H value negative in sign. Okay, so whenever there is an exothermic reaction, delta H value, whatever the value is, the sign will be negative in front of that. Whatever the value, if the sign is positive, positive X, let's say, okay, negative X, let's say. So negative is exothermic, positive means endothermic. And one way of estimating the delta H for a reaction is by keeping track of the total enthalpies of bone broken and the enthalpies of bones formed. I will show you in a next slide, a coming up slide. So for now, to understand how to classify certain reaction into exothermic and endothermic. Okay, exo means out, heat is, energy is out, and endothermic is you have to input the energy, right? So energy given and taken, it can take place in the form of heat. Okay, so we will be talking about heat on the reactions. Okay, so endothermic reaction means heat is energy, right? So heat is absorbed. Exothermic reaction, heat is released. On the sign of delta H, it will be a positive for endothermic, negative for exothermic. Okay, and during a endothermic reaction, the bonds broken in the reactants will be stronger than the bonds formed in the product. Okay, that's why it will be a positive number. In the case of exothermic, the bonds formed in the product are stronger. Okay, products are more stronger than the bonds broken in the reactant. That's why they are more stable, right? And delta H is negative. So products are higher in energy than the reactant in endothermic. Products are lower in energy than the reactants in the exothermic reaction. Okay, so that is the difference between two reactions. We will draw the energy diagram and we will be more clear on this. Okay, most likely that will be in our second part because I have seen here a question that is related with stoichiometry. So let's see here. Sometimes we might be given a question, okay, an equation, the equation that has a delta H incorporated with it. We call such equation a thermodynamic equation. Okay, the regular equation you see here, right? And the regular equation has some added information. It says, talks about the energy changes. Here delta H is negative 92, right? It means when the nitrogen and hydrogen, these two guys combine to form the product ammonia, side by side, the energy will or the heat will also be released. Okay, you can write ammonia plus heat over here, right? That heat released and the magnitude, the value of that heat is 92 kilojoule per mole. Okay, so is the reaction endo or exothermic? Right away you know this is a negative sign. Delta H is negative sign, right? It has a value with a negative sign. Whenever it is negative sign, it is exothermic reaction. Memorize that, okay? Because I already explained, now I'm saying memorize because you have already understood it, okay? Now, let's work on this question. How much heat would be released if 2 moles of hydrogen react? Let's say, how much heat will be released if 2 moles of hydrogen react. Just like we had been working with the relationship converting from moles to moles in earlier chapter, here we are going to relate the moles with energy value. Okay, what information do we get from this equation is when 1 mole of nitrogen reacts, it will release this much heat. When 3 moles of hydrogen react, it will release again the same amount of heat. Or I can say when 2 moles of ammonia is formed, it is a product, so it has to be formed. When 2 moles of ammonia formed, this much amount of energy is released. So I can use that relation as a conversion factor. Okay, I can write 1 mole of nitrogen is equivalent to minus 92 kilojoule per mole. Right, now I can make a conversion factor from this equality. Similarly, I can write 2 moles of ammonia is equivalent to negative 92 kilojoule per mole. Right, if the question is something related with ammonia, I can do that. I can also write 1 mole of hydrogen. Oh, I have 3 here, so I have to write 3. Okay, let me correct that. 3 moles of hydrogen is equal to negative 92 kilojoule of mole. So what I'm doing is I am relating the species, either reactant or products, with the amount of heat that is released. Now let's work on this problem. Now you have the equivalent equality. Now we can make the correct conversion factor and work here. 2 moles of hydrogen. Right? How much heat is released? So the released heat I have to write. So I'm going negative 92 kilojoule of heat on the top. What is the relation? 3 mole is equivalent to that number. So I write 3 moles on the bottom. 3 moles of hydrogen. Now I can cancel the mole of hydrogen, right? And I will have a number 2. Let me do it on the calculator. 2.0 times 92, divide that by 3. This gives me 61.3 kilojoule, and it is a negative sign here, so I will write that. It is a 2 sig fig, so I can write 61 kilojoule. Okay, so this much energy is released. You can say 61 kilojoule of heat would be released, or you can directly write the answer negative 61 kilojoule. Both mean the same thing. Okay, you just have to understand that negative sign means that much amount of energy is released. Got it? So now let's try the last question. How much of heat would be released if, well, 7.5 moles of ammonia? You can work on this. Please pause the video and you can work. I'm going to write it here. 7.5 moles of ammonia. And how much heat? So heat should be on the top. Okay, ammonia should be bottom. So moles of ammonia. The balanced chemical reaction gives me 2 moles of ammonia will be produced whenever you have negative 92 kilojoule heat also produced. Right? They are related. Now I can cancel the moles of ammonia and then I have kilojoule. The answer is 7.5 times negative 92 divided by 2. So let me do this. 7.5 times 92, divide that by 2, gives me 345. So it gives me negative 345 kilojoule. If I want to write this, 7.5 is 2 sig fig. So I can write minus 350 is my 2 sig fig answer, right? That much heat is released when 7.5 moles of ammonia are formed. Okay, so Let's move on. We can actually calculate the delta H values when we are given how much energy we had to add while breaking a bond, right? Total number of bonds in a reaction, and how much energy is released when total number of bonds are formed. So we can use actually the mathematical relationship given here. Delta H is equal to summation of, means sum of all the bond enthalpies of all bonds broken minus summation of all the bond enthalpies of all bonds formed. So you have to sum up all the enthalpies related with each bond that are broken, and you have to subtract with all the sum of all the enthalpies of the all bonds that are formed. Okay, bonds broken minus bonds formed, and these bond enthalpies are actually already calculated, so we have a data table for them. So we generally get those numbers in a table. Okay, we don't have to calculate, we just have to plug those numbers in this formula. Okay, this is something that you might do in your coming up class. Okay, today we just want to understand that there is a way of figuring that out. Okay, we can get to the number from the data and plug them to find the delta H, and that delta H indicates the relative strength of the bonds broken and formed in the chemical reaction. So in the data table here, okay, one important thing that we may need to get is, if you see this much energy, all this energy will be required if you want to make the bond between these two stuff here. Okay, let's take one example. If you want to make the bond between two hydrogen atoms, then you need to supply 436 kilojoule per mole. Okay, similarly, if you have a hydrogen molecule, okay, if you have a hydrogen molecule, this is a Lewis structure of hydrogen molecule, and you break down that bond, then that much of energy will be released from there. Okay, so delta H will be negative 436 kilojoule per mole in that case. One more thing we learn from here is, generally the multiple bonds or double bonds are always stronger than single bond. Okay, triple bond are stronger than double bond. Let's take one example here. You have carbon-carbon bond. It has 350 value. Carbon-carbon double bond. Now, in order to make a double bond, you have to supply more energy, 611. Okay, if you want to make carbon-carbon triple bond, now 3 bonds are there, further greater value of energy you have to supply. Okay, so in general you can say triple bond is stronger, that's why you need to supply more energy to break that, right? So let me write here, triple bond is stronger than double bond, and double bond is stronger than single bond. Okay, we can compare that between carbon-carbon, or you can compare between carbon-oxygen, or you can compare between nitrogen-nitrogen. Okay, you can take any similar comparable things. Okay, so here we have nitrogen-nitrogen triple bond. Here we have nitrogen-nitrogen single bond, right? So do we have nitrogen-nitrogen double bond? I do not see it here. Okay, but you can see we have a single bond here, we have a triple bond here. Triple bond is much stronger than the single bond. Okay, yeah. So we will learn about the rates of reaction, learn more about the energy diagrams in the coming section of this class, okay, coming portion. So thank you.